Hello everyone! The topic for this lecture is attack detection and prevention, where we will look at different methods that can be used to detect and prevent attacks on web-based information systems. Security event logging, when implemented correctly, is one of the most effective ways to detect attacks against the system. Monitoring tools can use these logs to trigger alerts, and logs also provide valuable forensic evidence during incident response. Usually, there are a couple of log data sources available in a system. Operating system logs contain events related to system activities. These logs are mostly relevant only if attackers have already gained system-level access to the server. Web server logs, on the other hand, should record every HTTP request received, making them useful for reconstructing events and understanding what an attacker attempted to do. Most web servers generate an access log, which by default records the client's IP address, requested resource, referrer if available, and the user agent header. However, these logs do not include the body of post requests or request headers. Therefore, this type of logging is insufficient from a security standpoint, as it fails to provide the full context of the request. Then there is also the error log, which usually contains errors and warnings from PHP code execution. Monitoring this file is a good practice, as these errors often point to bugs or handling of unexpected user input. Then, aside from web server logs, the web application can and should produce its own logs. Since the web application has full access to the entire security context of the request, the web application should be the primary source for generating security event logs. So what events should the application log? To detect hacking attempts at the earliest stage, all input validation failures should be logged. Here is an example of how we could do that. So here we check whether the request's action parameter is among the whitelisted values. If it is not, we log a warning stating that we failed to validate the action parameter, logging the invalid value as well. And we can apply this to all parameters received. To reduce false positives, we must ensure that client-side checks prevent a user from submitting invalid values. That way, when such an event is logged, we know for sure that this is a hacking attempt where someone has bypassed the client-side validation checks. Similarly, we should log all access control failures, as this will indicate that someone is trying to bypass authorization checks implemented by the application. Then we should log all authentication attempts, both successful and failed. Then we should log all administrative actions, such as password changes, account creation, role changes, file uploads, and any critical transactions. So this will be very application and business logic specific. Here we have to ask ourselves what events would help us investigate fraud or a system compromise. So in case we have been compromised, logs should help us answer how we were hacked and what the attackers did. We might also want to log as many types of anomalies as possible, especially those caused by unexpected user behavior. For example, changing the browser's user agent during an authentication session, performing actions in an unusual order, at unusual times or at unusual speed, and so on. To come up with a list of anomalies that should be logged, we would have to deeply analyze the business logic of the application. Unfortunately, real-world applications rarely attempt to log anomalies, even though doing so is an effective way to detect early signs of hacking. Anyway, the next question is what event attribute should we log? To be useful, each log event must provide enough context to answer the key questions: who performed the action? If authenticated, log the user ID, otherwise at least the IP address. What security-relevant action did the user perform? Where in the system did it happen? When did it occur? A precise timestamp is crucial here. And finally, if possible, why did it happen? Though that is often hard to determine. Let's look at an example of a log entry. Using the JSON format here is a good idea, as it allows structured storage and is easy to process. So a typical log entry should include a timestamp with standard formatting and explicit time zone information to avoid any ambiguity. Then an event ID, which helps us to uniquely identify the event, as the timestamp may not be unique. Then an event code like authentication login success. This helps us to easily search for events of the same type. Then a severity level for each event helps define its importance. Severity levels here could be info, a warning, error, fatal, alert, or similar. Logging the severity level allows monitoring tools to alert us only about high severity events, for example. Then a description of the event, such as user John Doe login successful. Client details, such as the IP address and the browser's user agent field. Then a user ID, if we are able to connect the event to a specific user. This helps us quickly search for events related to a specific user. Then the session ID of the user session to identify the specific session in which the event takes place. Note that if the session ID is the same value which is used in session tokens such as authentication cookies, then such an ID is considered a secret and should only be logged in an irreversible form, meaning that we would have to hash it. Otherwise, anyone who sees the log entry could potentially hijack the user's session. Because of this, and because session tokens may be regenerated during a single login session, it may be better to use a separate session identifier here, distinct from the one that is used in session tokens. Then a request URI and method to identify the request that triggered the event. And here we can also include the application file and function name involved. This allows us to easier trace the issue back to a specific function of our application. As you can see, here we have quite a few data attributes to log for each event. Therefore, it is a good idea to implement the logger in a way that it automatically captures most of this information from the runtime environment. That way, we only need to manually pass data the logger cannot gather on its own. For instance, we would not pass the IP address here, as this information the logger function can obtain on its own. When implementing the logging mechanism, we must ensure that it is not vulnerable to log injection and log exhaustion attacks. So first, we have to encode the user input we log to prevent it from breaking the structure of our log files. For instance, this code would be vulnerable if this log entry were written into a line-based log file, as the attacker could inject new line characters and log field delimiter characters, effectively injecting additional log entries into the log file. This type of injection can be used to trick our log parser and bypass our security monitoring measures. As a countermeasure, here we can encode the user input using the URL encode function, for example. Alternatively, we can use base64 encoding, but that makes logs harder to read. Then we must also ensure that our logger cannot be abused to exhaust our system resources by filling up disk space. So here it can be dangerous to log the entire user input, as depending on the server configuration, the value here can be megabytes long. As a measure, we can log only the first 1,000 characters of the invalid input, as this is usually sufficient for log analysis purposes. A crucial point here is that detection requires monitoring. It is not enough to simply log attack events. Someone must monitor these logs and respond when security-critical events occur. Alert triggering rules may be very helpful here, as there are many log analysis tools that provide a feature to define complex rules for when an analyst should be notified. For instance, a single authentication failure may not require notification. However, many authentication failures in a short time could indicate a brute force attack requiring notification and quick response. Secure log storage is another important aspect. Since logs may contain sensitive user data, the classification level for logs should be the same as that for the data stored in the information system. In practice, however, it is common to forget that logs must be protected as rigorously as the user data that is stored in the database. Another consideration is that we want to prevent an attacker from tampering with the logs. For this reason, preferably, logging should be done to a remote append-only database, such that even if the application server gets fully compromised, the attacker cannot destroy or modify already logged events. The fact is that logs that can be trivially modified or deleted are not very helpful for investigations and prosecutions. Regarding the logging of sensitive data, the rule is that sensitive information such as passwords should never be logged, not even passwords from failed login attempts, as these can reveal partial information about the correct password. As we discussed earlier, passwords, to the extent possible, should be protected even from the server itself. There may also be legal requirements specifying what must be logged and, more importantly, what personal data must not be logged, or if logged, after what period of time it must be deleted. Under GDPR, the IP address alone is considered personal data, as it can be used to identify an individual. This means that even the default logging performed by a web server falls under data protection laws and requires a valid legal basis. The current understanding is that as long as this logging is performed for security purposes, it may fall under the legitimate interest exception and may not require user consent. So the purpose of the logging is important here, but we must also demonstrate that we followed the data minimization principle, which requires processing only the minimum amount of personal data that is necessary to achieve the intended purpose. But we will not delve further into this topic. Anyhow, to summarize, when developing a web application, security event logging must be built into every functionality added to the application. This, however, requires careful thinking about what to log and how much data to log for each event. A web application firewall, or WAF for short, is essentially a firewall for HTTP traffic. It filters and monitors requests based on predefined rules. Let's take a closer look at ModSecurity, which is one of the most popular open-source web application firewalls. Originally, it was developed as a module for the Apache web server, but today it also supports Nginx through a connector module. When installed as a server module, it intercepts and monitors HTTP requests and responses as they pass through the server. While we will focus specifically on ModSecurity here, the same concepts also apply to many commercial WAFs, some of which even support the same rule language. So let's look at how to write some simple ModSecurity rules. Suppose we want to block requests that attempt to exploit a cross-site scripting vulnerability on our website. Here's a common example of an XSS payload that injects a script tag. Here's how we might write a rule to block such a request. To define a rule, we must use the secrule keyword, then specify the variables we want to inspect, the pattern to match, and then the actions to perform if a match is found. In this case, we inspect all get and post parameter names and values, and all request header values. We check whether any of these variables contain a script tag, and if they do, we log the event and block the request before it reaches the web application. And it is also necessary to specify a unique identifier for each rule. So this basic rule is quite powerful as it can block XSS attempts whether the payload appears in query parameters, form fields, or headers like user agent or referrer. Now the problem is that this rule can be easily bypassed if the attacker uses uppercase letters here in the tag name. To fix that, we can apply the lowercase transformation to normalize the input before matching. But even then, the rule can still be bypassed by adding a whitespace here after the tag name. To address that, we can apply the remove whitespace transformation on the input. So now it should be fine. The rule should be able to detect the script tag as long as it does not have additional attributes. Such generic rules, however, may trigger false positives if our application allows legitimate input that includes the script tags. So we would need to adjust this rule to apply only to specific parameters or not to be applied to parameters that are allowed to contain script tags. Also keep in mind that a WAF does not have any knowledge of our application's internal logic. it does not know which parameters our web application expects in a request. Therefore, WAFs can often be easily detected by simply sending a request with some dummy parameter containing a known attack string. And if the request is blocked, it is a good indication that a WAF is in place. Then, ModSecurity also supports rule chaining that can be used to combine multiple conditions into more complex logic. The chain action must be specified for all rules except for the last rule in the chain. In this example, we are using a chain rule to block spam. So, if the request file name matches form.php and the request method is post, then we apply this regular expression to the request body, and what it does is that it searches case insensitively for these specific strings that commonly appear in spam comments. If any of the strings are found, the request is blocked. Another good example is this simple rule that can be used to block admin logging attempts from unauthorized IP addresses. So, if the username parameter contains admin and the remote address is not equal to this IP address, then we block the request. Of course, this kind of logic could be implemented in the web application itself, but there may be cases where we need to enforce security without modifying the application code. For example, if the web application is developed and maintained by a third party. So, a web application firewall can also be used for virtual patching to block exploit attempts before an official patch has been released by the developers. Note that ModSecurity is not limited to inspecting requests only. It can also inspect and block HTTP responses returned by the web server. For example, here is a rule that inspects the response body looking for the string tag trace in it. If a match is found, the response is blocked with a 403 forbidden status code preventing leakage of potentially sensitive debug information. So in this case, the application still processes the request as normal, but the response never reaches the client. Note that here we need to specify phase 4 because by default, rules run in phase 2, which is the phase when the request has been fully received by the server, whereas phase 4 is the phase when the response is also available to the server. So in essence, this is how ModSecurity rules are constructed. ModSecurity provides a long list of target variables that can be inspected by rules. As you can see, there is basically a variable for every single thing that can exist in an HTTP request and response. Then there are quite a few transformation functions that can be applied to the variables. Two of them you already saw here in this example. Then there are different types of operators that can be applied. On strings, we can apply regular expressions, fast pattern matching, and check whether the variable is equal to, begins with, ends with, or contains a string we are looking for. Numerical values can be compared using these operators: equal to, greater than or equal to, greater than, less than or equal to, and less than. If a variable is expected to contain XML data, we can validate it against the schema or a local document type definition. And then there are also other interesting operators which can be used to check an IP against a real-time blacklist, perform a geolocation lookup, inspect file can be used to check uploaded temporary files for viruses. The Lua operator can be used to execute a script written in the Lua programming language, verify CC to detect credit card numbers, and verify SSN to detect US social security numbers. As for actions, we can block requests in two technically different ways. Deny will block it by returning an HTTP error response, while drop will silently terminate the TCP connection without sending a response. The redirect action can be used to redirect the client using the location header. The proxy action can be used to forward the request to another web server, for instance, to a honeypot server. And the allow action explicitly allows that request triggered by the rule. The log action logs the event into the server's error log, while the audit log action triggers writing a full audit log entry for the transaction. So for audit log, we can specify in the ModSecurity configuration where to write the audit log and which parts of a transaction to include in the log, each letter here corresponding to a specific part to log. And here we can see the description of each letter. So using the audit log action, we can log request headers and the full request body, as well as the response body and headers. So this is a powerful logging capability, which is usually not provided by the web server. But okay, the sanitize arg action can be used to mask sensitive data when it is logged. The setVar action can be used to set and increment variables, and setEnv action to set environment variables. And finally, the init call action can be used to initialize persistent storage. Persistence here means that the data will be available across multiple requests. So this can be used, for example, to keep track of IP addresses, sessions, and users across multiple requests. To summarize, ModSecurity offers a flexible rule language that lets us write very powerful rules that can implement quite advanced logic. Alright, so we can write our own rules specific to our application, or we can also take advantage of publicly available rule sets that provide generic protection against common attacks. For instance, we can use the core rule set maintained by OWASP. The OWASP Core Rule Set contains a collection of high-quality rules that cover different types of attacks. These rules have been tuned to minimize false positives and are constantly updated to detect new attack techniques and fix rule bypasses. Let's go over these rules one by one to get a quick overview of the types of attacks that they can detect. Method enforcement rules block requests that use HTTP methods not explicitly allowed. Scanner detection rules identify automated vulnerability scanners based on a database of user agent strings used by popular scanners. And this, of course, can easily be bypassed by modifying the user agent header used by the scanner. Protocol enforcement rules detect various types of HTTP protocol violations in incoming requests. These violations can indicate non-compliant HTTP clients or exploitation attempts. For example, they can detect missing, empty, or invalid headers, invalid or non-printable characters in the request, too big values, or headers not allowed by the configure policy. Protocol attack rules attempt to detect header injection attacks by looking for line breaks in request headers. They also identify HTTP parameter pollution by checking for duplicate request parameters. Multi-part attack rules detect malformed and malicious requests in multi-part form submissions. Local file inclusion attack rules detect path traversal attacks by looking for traversal sequences in the request, and they also attempt to detect operating system file access and restricted file access by matching strings in a request against the database of file names that attackers typically try to access either directly or through local file inclusion vulnerabilities. Remote file inclusion attack rules detect attacks by looking for protocol schemes and IP addresses in request parameters. Remote code execution attack rules attempt to detect shell and command injection by looking for shell-specific character sequences, as well as checking against the database of common commands used in Linux shells and Windows PowerShell. These rules can also detect attempts to upload files with forbidden file names, these file names being in the backlist. PHP attack rules aim to detect PHP code injection by searching request parameters for anything that looks like PHP code. They use databases of PHP configuration directives, function names, and variable names. Java attack rules cover the Java programming language using a database of common Java classes often involved in attacks. Then there are also generic attack rules to detect Node.js, Ruby, and Perl specific attacks. These rules also try to detect server-side request forgery attacks, by using a database of URLs frequently used in SSRF attacks. Cross-site scripting detection rules essentially look for HTML tags and attributes commonly used in XSS payloads. They also handle various evasion techniques attackers might use to bypass XSS detection. SQL injection rules check user input for SQL language statements, operators, functions, and common database names. They also handle different SQL injection evasion techniques. So if these rules are enabled, it becomes much more difficult for an attacker to successfully exploit an SQL injection vulnerability. And finally, there are session fixation detection rules. These rules look for HTML code that sets cookie values using JavaScript, as well as session ID parameters passed in the URL or post request parameters. So these are the CRS rules that detect attacks by analyzing HTTP requests. In addition to that, there is also a set of rules that detect data leakage in HTTP responses returned by the server. These rules can detect directory listings returned by the server, error messages and stack traces returned by SQL engines, Java and PHP applications, and also Java and PHP source code leakages, which can be detected by scanning response bodies for language-specific keywords. Here, a database of SQL error strings is used, also a database of PHP error strings, and for Java code leakage, a database of Java-specific keywords is used to identify cases where Java application source code might be exposed. Alright, so this is all very powerful and helpful, but the problem is that if we enable all these rules out of the box, we will immediately get thousands of false alarms. Because these rules are looking for a bunch of keywords that may appear in a request or response also for a legitimate purpose where there is actually no attack happening. So we will need to tune this rule set carefully to reduce false positives and make it work effectively for our specific web application environment. So there are several approaches for handling false positives. First of all, initially we would run the ModSecurity engine in detection-only mode, meaning that it would not block requests if a rule is triggered. Only after we have minimized false positives, we would switch to blocking mode. If we see that a particular rule is generating false positives, we can remove it by its ID. Even better, we can patch the rule by adding an exception for the specific variable that triggered the false positive. For example, here we added an additional condition to the rule so that it does not apply to the parameter WP-post, which is a parameter used by WordPress. Then we can also disable all rules that have a specific tag. Here we disable all rules related to SQL injection, which might make sense if our web application does not use SQL at all. So the rules in the rule set are tagged using various labels that describe the attack type, platform, and programming language involved. We can use these tags to customize the rule set for our specific environment. In addition, there are rule exclusion packages for WordPress, Drupal, Nextcloud, DocuWiki, and other popular web applications. These packages essentially adjust the rule set to work around false positives for these specific web applications. Another important concept is paranoia levels, which are assigned to each rule. We can configure the rule set to operate at a specific paranoia level, ranging from 1 to 4. Level 1 is the most lenient, generating the fewest false positives but missing more advanced attacks. Level 4 is the strictest, enabling all rules but increasing the chance of false positives. We can choose the paranoia level based on how sensitive our web application is and how much time and effort we are willing to invest into fighting false positives. Anomaly scoring is another mechanism provided by the core rule set. It can be used to block only those requests that exceed a predefined anomaly score threshold. The idea here is that each triggered rule increases the anomaly score for that request. We can configure our setup to block only those requests that reach a specific score. Most rules add 5 points to the score. So if we set the blocking threshold to 5, any request that triggers a rule will be blocked, except for some protocol violations which increase the score by less than 5. If we raise the threshold, for example, to 10, then at least 2 rules must be triggered for the request to be blocked. SQL injection attacks typically trigger multiple rules, whereas other attacks may trigger just 1 rule. So we need to decide whether we are comfortable blocking requests with low scores, which are more likely to be false positives. Then there are also various plugins, which are essentially rules that have been moved out of the default rule set for optional use. For example, the FakeBot plugin detects bots that spoof user agent strings to impersonate known bots like Googlebot. The plugin performs a DNS-based check to verify if the request actually comes from a legitimate crawler. The Body Decompress plugin enables on-the-fly decompression of HTTP response bodies if compression is applied by the web application. ModSecurity by default does not handle decompression, so this plugin must be enabled manually. And finally, the Denial of Service Protection plugin can count requests from an individual IP address and apply rate limiting if a configured threshold is exceeded. Anyhow, to summarize, enabling the OWASP Core Rule Set makes it significantly harder for attackers to exploit even trivial vulnerabilities. The trade-off is that it requires careful setup and ongoing maintenance unless we are okay with occasionally blocking legitimate requests that trigger the rules by mistake. Let's quickly touch the subject of protecting our website against a distributed denial of service attack. The most effective and also the simplest method is to put our website behind a content distribution network or CDN. Here is an illustration showing what happens when no CDN is used, where thousands of compromised computers around the world are bombarding our web server with requests. Note that these do not have to be HTTP requests. They can be any type of network traffic. It does not matter how fast our server is. At some point, the capacity of our network bandwidth will be reached, and our server won't be able to receive and serve legitimate requests anymore. When we put our website behind a CDN, the CDN acts as a reverse proxy server forwarding HTTP requests to our server, which is called the origin server. For this to work, we would need to point the domain name of our website to the IP address of the CDN. An interesting thing here is that even though there may be just a single IP address associated with a CDN, in practice, this IP address may be shared by hundreds of CDN data centers all over the world. Thanks to how IP address routing works on the internet, the network traffic is routed to the geographically closest data center, distributing the attack traffic to data centers all over the world. In essence, we are fighting a distributed attack by distributing the destination of the attack. Note that it is important to keep the real IP address of our server private, as otherwise the attacker could bypass the CDN and attack our server directly. So the task of the CDN here is to absorb the incoming attack traffic and only forward HTTP traffic to our server. If the attacker uses HTTP requests to attack our website, the CDN can apply rate limiting and block the attacking IP addresses. In addition, the CDN may offer web application firewall capabilities, enabling us to block HTTP requests based on certain characteristics. To fight bots, the CDN can apply JavaScript and captcha challenges, blocking requests unless these challenges are completed. The key point is that these challenges are solved by clients interacting with the CDN, so the origin server is not involved in this process. This ensures that only legitimate human traffic reaches the origin server. The CDN will also often cache and serve static content from the origin website. This way, the origin server is only hit with requests that require returning dynamic content to users. So this offloading helps improve the performance of the origin server even when serving legitimate requests. Note that we don't have to be super rich to afford such a service. For instance, Cloudflare offers unlimited DDoS protection in their free package as well. So basically, today, if a website is attacked by a DDoS attack, the simplest and cheapest solution is to simply move it behind a CDN and the problem is solved. And more websites today are moving behind a CDN. This, however, has some negative security implications because these content distribution networks become very powerful entities as they can inspect the decrypted HTTP traffic transmitted between the user and the origin website. So we must trust these CDNs not to abuse their capabilities. But okay, that's about DDoS protection. As the final topic of this lecture, let's discuss some aspects of security testing for web applications. One very useful standard for performing a security testing is the OWASP Application Security Verification Standard. It defines requirements for a secure web application and can be used as a checklist when performing a security assessment. The requirements are divided in 14 sections, and just to give you an idea, let's look at some examples from the session management section. Here you can see requirements for cookie-based session management with a focus on cookie attributes and security prefixes. The standard defines 3 levels of security. Level 1 is the minimum security level that any web application should satisfy. Level 2 is intended for applications that handle sensitive data. And level 3 is for the most critical applications, such as those in banking or financial services that deal with highly sensitive data and high-value transactions. Let's look at the requirements for session termination and how they differ between the levels. As you can see, level 1 requires terminating the session after 30 days, level 2 after 30 minutes of inactivity, and level 3 after 15 minutes of inactivity, and requires two-factor authentication for re-authentication. And here we can see that for the level 1 applications, there is no requirement to provide an option for terminating all active sessions. Now, to summarize, this security verification standard helps performing security testing in a systematic way aligned with the security level of the application. In fact, after completing this course, you should have the skills needed to apply this standard when testing web application security. Another important point to highlight is that it is useful to have a dedicated application security team of people whose job is to test the security of applications developed within the organization. Of course, every developer should also be trained to write secure code, but we cannot expect them to fully assess the security of their own work, as there is an inherent conflict of interest. After all, the developer's primary goal is to get the application running and not necessarily to analyze how their code might be exploited. Now, if we cannot afford an in-house team, then there are many companies that offer penetration testing services. So we can ask such companies to perform security assessment of our application. Pentesting is usually performed using one of these 3 methods: black box, white box, and the gray box method, where both black box and white box methods are combined. A black box testing is useful for simulating conditions of an external attacker that does not have any inside knowledge or access to the source code. However, black box testing may be more time-consuming and is unlikely to uncover all vulnerabilities in our code. Therefore, it may be helpful to share the source code with pentesters or to apply the gray box method, where pentesters first try to exploit the application without inside knowledge, and then after access to the source code is provided. Sometimes automated vulnerability scanning is used at the beginning of a test to quickly identify basic issues and get a baseline understanding of the application's security posture. After testing is complete, pentesters should produce a pentesting report describing the issues found and recommending mitigation measures. These reports are usually considered sensitive and are not made public. However, there is this nice repository of publicly available pentesting reports sorted by the companies that produce them. And it is interesting to see how the findings are worded and formulated. For instance, here is a random report that documents a missing parameter check. Note that pentesting can cover not only web applications but also other types of software and services. Now, another way to improve security is by launching a bug bounty program, which invites ethical hackers to find and report vulnerabilities in our web application. We can run our own bug bounty program or use a platform like HackerOne, where researchers from all over the world can participate and get paid for valid findings. In fact, some security researchers make a living by participating in these programs. Now, even if we cannot offer money for reports, we can implement a vulnerability disclosure program, which simplifies the process for security researchers to report issues. And in this regard, it is also a good idea to publish a security.txt file on our website, either under the well-known directory or directly at the root. This file should contain contact information for reporting vulnerabilities and may optionally include some other information such as an encryption key that can be used or a link to our security policy of a vulnerability disclosure program if we have one. And as a real-world example, here is the security.txt file from the Telia telecommunications provider. As we can see, they participate in the HackerOne bug bounty program. But alright, with that we conclude the final lecture of this course. Thank you for watching.